Good morning, students. This is today's review. Today's April 21st. For you, for me, it's the evening of April 20th. Today is a review of Euler's method. The reason we're reviewing Euler's method with you is because it is a BC-only topic. It's also a pretty easy topic to get, so it might be on your test, and if it is on your test, then I hope you get the points for it. So Euler's method is a method of taking a curve and approximating it as a straight line for a little bit, checking the slope again, making a new straight line, and then using that approximation for the curve. You can take as many steps as you need. You can make your steps as short as possible, but here's kind of a visualization of what you get with Euler's method. Oops. This is the idea. Your curve is curvy, but you're saying, okay, I'm going to treat it more like a dot to dot, and I'm just going to connect the dots. And treat it as linear, even though it's clearly not linear, and just use that approximation. But instead of saying, I'm always going to treat it like the same line, every once in a while you'll adjust and change your slope. So when you're using Euler's method, it's because you have a differential equation. I'm going to make up a differential equation. Let's just say we have the differential equation dy dx, which could also be written as y prime. It could be written as f prime of x. But you're given a differential equation with Euler's method. Let's say that ours is 2x minus y. And let's say that we also know that for the solution that we're looking at, f of 1 is equal to negative 2. So we're given a starting point, and we're given a differential equation for our curve, but we're not given the curve itself. So we can't follow the curve itself in order to get what our new point is. And we would like to know, what is f of 2? And we would like to do it in 2 steps. Okay, this is all just a problem I made up. I would like to take 2 steps to approximate f of 2, and I'm going to use this differential equation. So this is just to remind you of how Euler's method works. This is the one that I did as a table. So I always start with my x comma y. That's my starting position. And then I'm going to calculate the slope using the differential equation. Now this is going to be a number answer rather than the differential equation answer, and it's going to change depending on where I am on the curve. I'm also going to need a delta x, and I'm using the delta sign because it's not an infinitesimal change in x. It is a measurable change in x because we're taking just 2 steps to get from x equals 1 to x equals 2, so we're not taking an infinitely tiny step, we're taking a measurable step. And then we're also going to have a delta y. Delta y is how far we change our y-coordinate if we change our x-coordinate this far. In order to get delta y, you're always going to multiply your dy dx times your delta x. So your initial point is 1 comma negative 2, so I'm going to put that in my table. Given that this is our differential equation, that means that our differential equation would be 2 times 1 minus negative 2. So our slope becomes 4 just at that point, not everywhere on the curve, but at that particular point we have a slope of 4. We're taking 2 steps. We're going to get from x equals 1 to x equals 2. That means each step is going to be a half wide. And then delta x, our change in y, is going to be delta x times delta y is going to be delta x times our derivative. So 4 times 1/2 would be 2. So for every half of a step we take in the x direction, since our slope is 4, we're going to take a step of 2 in the y direction. If our slope is 4 and our rise is 1/2, our run would be 2. Okay, so then we look at what is our next point. Well, our next point, because we have a delta x of 1/2, would be at 1.5. And our y-coordinate started at -2 and had a change of +2, so our y-coordinate is now 0. Then we go back and calculate our new slope. Our new slope would be 2 times 1.5, which would be 3, minus 0. So our new slope is 3. Our slope looks like it's decreasing. Our slope is changing. It's getting smaller. Our delta x is still going to be 1/2 because we still need 2 steps in order to get a distance of 1. But our delta y isn't going to be the same anymore. It's just going to be our slope is 3 and our rise is 1/2. So that means that our delta y would be 1.5. And that means that if I get to an x-coordinate of 2, my y-coordinate is going to be 1.5 because 0 plus 1.5 is 1.5. And so if I want to use Euler's method to estimate f of 2, the estimation would be about 1.5. I know that's not perfect because I estimated it with straight lines and it was a curve, but I also know that it's a pretty good estimate and better than just using one single tangent line to estimate the curve. And I can also say, well, is that an overestimate or is it an underestimate? And the way we decide that is we look at the concavity of our original function. So if the original function is concave down, like a frown, then all of those individual tangent lines are going to lie above the curve. So that means that we would have an overestimate. If instead our curve is concave up, then all of those individual tangent lines are going to lie below the curve, so we'd have an underestimate of the actual value. The way we figure out whether our function is concave up or concave down is we would look at the second derivative. So we'd say, well, I know the first derivative, dy dx, is equal to 2x minus y. So that means that the second derivative would be 2 minus dy dx. Well, our dy dx is always bigger than 2 for our particular function. So we have a situation where we have 2 minus a number bigger than 2. So these are always going to be greater than 0 for our situation. I'm sorry, I lied. They're always going to be less than 0. And so we have a concave down, like a frown. And that means that all of these tangent lines that we drew were just a little bit higher than our curve. And so this would be an overestimate. And I know that the value of f at 2 is actually less than 1.5. All right, that's a quick overview of Euler's method.